Okay. Okay, so let's again look at this. So some facts about singular value decomposition. So A of course has a singular value decomposition, let us say U sigma V transpose. Now this just means that A is M cross T. This just means that you can write this as follows: sum over I equals 1 to D sigma I Ui Vi transpose. Now this product can be rewritten like this, where these sigma i's are our singular values, and Ui Vi transpose Ui Vi transpose is a rank 1 matrix. This is a rank 1 matrix, and now what we are essentially saying is that we are summing up D different rank 1 matrices and scaling them appropriately, which is sigma i's. So if you sum up 2 rank 1 matrices, the matrix that you will get will be at most rank 2. So if you sum up D rank 1 matrices, the matrix that you will get will be at most rank D, and that's what this essentially says, right? So in this case you will get an exactly I mean, if sigma i's are all positive, so you will get a rank D matrix because you are summing up D rank 1 matrices. Okay, so now one way to define norm, right? So the norm of a matrix, the L2 norm, we know how to define L2 norm of vectors. One standard way to define L2 norm of a matrix is to talk about the largest singular value of the matrix. Right, so this is the definition that is commonly used to say what is the L2 norm of a matrix. And we would need that later to see how good our approximations is, right? So when you are measuring distances among matrices, between matrices, you want to measure it in a certain norm, and then the standard norm to use is the L2 norm, which is nothing but the largest singular value of the given matrix. Let's say we care about the best rank K approximation of A, right? So what do I mean by that? Let's say here is what I want, right? So what is the best rank K approximation of A? So the setup is the following: you are given this matrix A, which is M cross D, which is potentially rank D, and D might be large. And now I am asking the question that, well, if I want a low rank approximation for A, right? So where the low rank that I am allowing is only up to K, then what is the best low rank K approximation of A? Now, how do we measure approximation? And that's where this norm plays a role. So which means that we are asking among all matrices B such that the rank of B equals K, give me the B such that, you know, I want the argument that minimizes the following quantity, right? The distance between A and B in the L2 norm sense, right? So what I'm asking for is, right, so that B star, which is the approximation of A, but has only rank K, right? So now how am I measuring approximation? Well, I'm going to take the difference matrix and look at its L2 norm. that is, we know L2 norm is just the largest singular value of the difference matrix, right. So, this is then asking among all matrices B such that rank of B is K, give me the one that has the largest singular value for A minus B. Now, the great result of linear algebra is that, you know, this problem is easy to solve, right. Now, you can, if you think of this as a problem where, you know, you are trying to optimize an objective function over the space of all rank K matrices. Now, it is not a convex problem. It is not any simple, you know, constraint set here where you are looking at the set of all matrices which have rank K. So, even if I say rank, you know, so, I mean, if I give you an exact rank K, so the set of all matrices which have rank K, you know, do not form a convex set. So, this is in a standard convex optimization sense, this is actually not an easy problem to solve. But the great result of linear algebra is that this is in fact an easy problem to solve, and the actual result for this is given by the singular value decomposition that we already know, right. So, in fact, B star is just the following. So, if A equals sum over I equals 1 to D sigma I ui vi transpose, that is A singular value decomposition is u sigma v transpose, then B star is just sum over I equals 1 to k sigma I ui vi transpose, right. So, if A is the original A is sum over I sigma I vi transpose, of course, the convention here is that sigma 1 is greater than or equal to sigma 2 greater than or equal to sigma d, right. So, sigmas are always arranged in decreasing order. The largest singular value sigma 1, the smallest is sigma d, right. So, A might be a rank D matrix. Let us say M is, just to set some numbers, let us say M is 1000, D is 500. So, A is a 1000 cross 500 matrix of rank 500. Now, we are asking what is the best rank 10 approximation of A in the L2 norm sense. Then the answer to that is, you know, you do the SVD of A, take the singular values, make all singular values from 11 till 500 0, and then reconstruct the matrix, right. So, in other words, you take only the top 10 singular values and their corresponding singular vectors u's and v's, and then add up those k rank 1 matrices, you will get a rank k matrix, and that is in fact the best rank k approximation for A. This is a famous theorem in linear algebra. So, this is great. So, which means that, you know, this again ties up neatly with our low rank approximations, right. So, because though A may not be low rank, if I want if I want a low rank approximation of A, then I better do SVD, right. So, that's precisely what this theorem is telling me. Now, how do I do this, right? So, of course, with a computationally in a computationally efficient way is the question that we are after. Now, here is a potential way to do this computationally efficiently, and let us see if this makes sense, right. So, how to perform SVD computationally in a computationally efficient manner. So, this is the question that we are asking now. Okay. So, let us say for the moment somebody tells us the top k eigen or singular vectors of A, the left singular vectors, the u's vectors, right. So, so there are m vectors in u1, u2 till um, if you remember, and then there are V1 to VD. Let's say somebody tells us, say we are given U1 to UK. Remember, this is also an orthonormal set. It's not a basis, but it's an orthonormal set, right? So, why is not a basis? Because there are m, you need, I mean, these are all m dimensional vectors. So, to have a basis you need m such orthonormal vectors, but let's say we are given k, right? Now what can I do with this, right? So, let's say I have access to U1 to UK. Now the question is, how can I do SVD quickly, right? So, to get a, let's say, a rank k approximation of a given matrix, that's what I want. How can I perform SVD faster is the question. So, here is a way to do SVD faster, right? So, now I have A, and which is, let's call these A1, A2 till AD. And I am given, let's call this matrix as Q, which is just the matrix with the vectors U1 till UK which are given to me. Okay, so this is given to me. Now remember, I want to do SVD of A, right? So, if I did SVD of A in the usual inefficient way, which takes m times d squared time, then I would have gotten U1, U2 till Um, and then sigma 1 till sigma d. The rest are zeros, so I am not filling the zeros, and V1, V2 till Vd. I would have gotten this had I done SVD naively. Naive SVD would give me this. Now I want to get this back. So now once I have this, then my low rank approximation is easy, right? So how would I do my low rank approximation? If I want to approximate using D, then I will just take U1, U2 till UK. I don't care about the remaining. Sigma 1 till sigma k, I don't care about. Here is sigma k, I don't care about these values, they don't matter to me, and I will do V1 till Vk. And now if I do this multiplication of these restricted matrices, this would give me the best rank k approximation to A. That's how I would do in a naive way, right? So I would do the SVD completely, get U sigma V transpose, and then take the top k left singular vectors of U, retain the top k singular values from sigma and top k right singular values from V, and then I would just multiply them, and I would get the best rank k approximation for A. This is the naive way. Now what I am saying is that in this method you are just given A, but now let's say you had access to this matrix Q which tells you the top k left singular vectors. Then can I do something better is the question. The answer is yes, and here is how you can do that. Now what you do is, you do the following. You compute, so here is a fast SVD given Q. Now compute Q transpose A. Yeah. So what is Q transpose A? What is Q transpose? Q transpose is going to have the rows as U1 till UK, and of course A itself, this is going to be A. So what I am essentially doing is I am taking every column of A and then projecting it onto each of u1 to uk. Because u1 to uk are all orthonormal, this means that I am taking every column of A and then I am computing the projections onto the subspace spanned by u1 to uk, right. So, that is precisely what I am doing here, right. So, now let's worry about the dimensions. A is m cross d, q transpose is just k cross m. So, q transpose A, let us call this some y is k cross d, okay. Now, what would this be like, right? So, this is my y. If I have to write, I know A has an SVD that depends on u also. So, if I do that, and just to see what I would get, what exactly is y, I know that this is going to be u1, u2, uk, and then it goes all the way up to um. I have sigma 1 to sigma d, and I have v1 to vd. That's this is my A, right. So, now when I multiply it with q, this is q transpose, this is A, what I am actually getting is, when I dot product u1 with u1, I will get 1, but then because this is an orthonormal set, if I do u1 times u2 or any other u, so I am going to get zeros. Similarly, for u2, I will get 0, 1, etc. until for uk, I will get 0 to till the kth guy, I will get 1, and then everybody else is 0. This is the matrix that I will get, and then sigma 1, everything else remains the same, right. Now, if I do the SVD of q transpose A, what will I get? Remember, q transpose A is a k cross d matrix. Y is k cross d. Now, if I do the SVD of that, what am I supposed to get? Well, in this case, what I will get is, the SVD of y should be some u tilde sigma tilde v transpose tilde, right. But what dimensions are these guys going to be, right? So, this is k cross d. So, this is going to be k cross k, this is going to be k cross d, and this is going to be d cross d, right. So, because y is k cross d. Now, what are those u tilde, sigma tilde, tilde, and v tilde, v hat tilde? What are those? Well, I know that they have to multiply to this, right, and these guys, this has these extra zeros, right. So, zeros that I do not really use at all, right. So, which means that this u tilde would just be, the identity matrix. Sigma tilde will just be sigma 1 to sigma k with the extra, zeros padded, and v tilde will exactly be my same v, right. So, I am removing this part, right. So, that is all I am doing, right. So, everything else is exactly the same for me, right. So, so what then I would get is, everybody else is 0 here. So, this would be my u tilde, this would be my sigma tilde, and this would be my v tilde, which is exactly v. Now, how much time does this take? Well, time complexity of this SVD, doing this step, time complexity, well, it is of order k times d, but now k is smaller, d is larger, right. So, earlier it was m cross d, m was larger, d was smaller. Now, it is, I have reduced this to k is much smaller. So, this is just going to be order of dk squared. That is the time that this is going to take. Well, this is still not the original SVD, right. So, or the original, I have still not gotten to this place yet, and that is because, I do not have this information yet, right. So, I only have u tilde sigma tilde looks exactly like how I want here, right. So, this is my sigma tilde. So, this is my V hat transpose, that is also stays, I mean I have recovered that with my SVD of doing for Q transpose A. But then this guy is U1 to UK, but what I have here is an identity matrix. So, how can I get back U1 to UK? Well, I know U1 to UK in this case, right. So, which is my Q matrix. So, what I would do then is to get the best rank K approximation to A, set B equals Q times, whatever U tilde I had here, right. So, Q times U tilde sigma tilde V transpose. Remember, what is Q? Q is just our bunch of K vectors, right. So, Q is Q just has the top K left singular vectors. So, when I multiply it with that with an identity matrix here, so all I am going to get is exactly the same top K vectors. That would just be what I really want, right. So which will be U1 to UK, right. So, this will just become U1 to UK, this will be sigma 1 to sigma K, this will be V1 to VK, well VD. The remaining are anyway not going to be useful, but anyway we would get that. So, what we have done is we have managed to do the following. We wanted the best rank K approximation to a given matrix A. The naive way to do that would take us md squared time. Now, what we said is, if we knew the top K singular vectors U1 to UK, then what we could do is we can project our data to U1 to UK subspace and now do an SVD in this lower dimensional space, which is a K cross D matrix. Instead of original M cross D matrix, we computed Y, which is Q transpose A, and we did the SVD here in this smaller dimensional space. Now, this will not give us what we want, but now we can again lift it back to the original space by pre-multiplying by Q, and then we will get what we want. That is basically the idea that we are talking about, right. So, if the other way to look at this is that you had A, and from A we did not work with the SVD of A. Instead, we said that we will first do Q transpose A, and then we got the SVD of that, and now then we pre-multiplied it by Q, and now this is all we have done, right. So, essentially we have done Q times Q transpose A. So, that is the matrix that we have obtained. The advantage is that instead of doing SVD of A, we did the SVD of Q transpose A, and so you got sigmas, you got V's, and now if you want the best rank K approximation, you pre-multiply by Q. So, now what is Q transpose? Well, because Q only has the top K eigenvectors, basically this is just the projection matrix onto the subspace spanned by Q. All we are then doing is that I am taking any vector A in the column, any column of A, and then projecting it onto the subspace spanned by the K top K singular vectors of A, left singular vectors of A, right. Now, then we are asking, what is this? Then this is in fact the smallest that you can get, right. So, this has to be smaller than any matrix, any let us call that some doesn't matter, I can project it onto any subspace and measure the the difference that I get, the best subspace to project on, so that you retain as much as of your norm as possible using these top k projections will be this guy, right? So in fact, we can say more. We can even argue what this value exactly is. What do you think this value is? This is a great question to think about to test your linear algebra skills now, right? So what are we saying, right? So A itself we know is sum over I equals 1 to d sigma I ui vi transpose. Q transpose A is kind of projecting A onto the top k left singular value space, which means that this is just sum over I equals 1 to k sigma I ui vi transpose. I am removing everything else, right? So from uk plus 1 till um, that part of the basis is gone. So I am only retaining u1 to uk. So this the difference would then be what? Well, this would just be the norm of sum over I equals k plus 1 to d sigma I ui vi transpose. Well, what is the L2 norm of this matrix, which is sigma k plus 1 uk plus 1 vk plus 1 transpose plus dot 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 till sigma d ud vd transpose. What would this be? Well, this would be the maximum singular value of this matrix, and because sigma is arranged in a decreasing order, this would just be sigma k plus 1. This would be the k plus first singular value, right? And now if it so happens in our data, right, so if I just plot the singular values, so singular values, rather if I just plot k versus sigma k, right, so the singular value might start at a large value, and then if it's exactly a rank k matrix, at k it will become 0, and then the remaining singular values are going to be 0. So this would be the situation for exact rank k, right? So if rank of k A is k, then this will be k, and then everybody else will be, well, k might not be 0, everybody after k will become 0, right? So let's say this is k. This would be when exactly you have a rank k matrix. Then all the other vectors are useless, which means that sigma k plus 1 will in fact be 0 in that case, which means that your best rank k approximation of A is A itself, because A itself is rank k, right? So that's what we are getting here as well, because sigma k plus 1 will be 0. On the other hand, if that does not happen, so then what we would get is the following. So if it is approximately rank k, which means to say that at k till k you have some useful information, and then after k the values become very, very small, right? So now this would be sigma k plus 1, which is a very small number, which means that even if I approximate A using a rank k matrix, what I get as remaining is, what I lose in this approximation is just sigma k plus 1, which is the k plus first singular value, which if the matrix is really approximately rank k, sigma k plus 1 is going to be small, and so are other sigmas, right? So I don't really lose much is the idea, right? So now what we have managed to do, let's be clear what we have managed to do. We started with asking how to do SVD quickly, and all we have said so far is that if we know u1 to uk, then I will be able to do SVD faster. How will I make it faster? Well, I'll first project all my I'll first take the dot products of all my columns with u1 to uk, which is to pre-multiply with q transpose. I'll do q transpose A, make an m cross d matrix a k cross d matrix, do the SVD for this k cross d matrix, and then pre-multiply by q to get back the rank k approximation. That is what I would do if I knew u1 to uk. and I save a lot of time because of doing this, because the SVD, the most time consuming operation does not happen in the M cross D matrix space, but it only happens for the K cross D matrix space. That's a great thing to do, but of course we cannot do this. Why? Because this assumes that we know U1 to UK. But this at least gives us a a direction to think about. If we somehow know U1 to UK, then we seem to be doing good in terms of time complexity, because we can reduce the dimension to K cross D, do the SVD there. Now the question is, who is going to give us U1 to UK? Nobody is going to give us U1 to UK, so it's simply not going to be possible to ask for what the SVD is giving to be a prerequisite to do SVD itself, right? So that's too much to ask for. Now here is the important fact to think about. Now, what essentially have we done is that by doing this pre-multiplication by Q transpose, doing the SVD for that, and then again pre-multiplying by Q, which means that essentially we have projected our data onto the top K singular value subspace, U1 to UK. Now, to do this projection, right, so we want to capture this subspace spanned by the top K singular vector, right. So for example, if that subspace was like this, right, so let's say it's a three-dimensional data, and then the subspace that we care about is this two-dimensional subspace, right. So let's say this was our subspace of interest. What subspace is this? Essentially, when I say this subspace, what I mean is the following. This is just the span of U1 comma U2, let's say, right. So maybe there are more U1, U2 till UM, but then I'm just looking at the span of U1 and U2, and now every vector I have, I might have some vector here, which is the column of A1. What I'm doing is I'm kind of projecting it onto this low dimensional subspace, right. So, and I'm going to think of this guy as A1 hat as my proxy for A. And now I'm going to match, project every column of A to this two-dimensional subspace given by U1 and U2. Now, if that is all I need, then I somehow need this subspace. I don't necessarily need U1 and U2 specifically. All I need is some basis for this subspace, right. So of course this U1 and U2 will be in this subspace. Maybe this is U1, maybe this is U2, right. So and then all linear combination of U1 and U2 gives me this subspace. But this is not the only orthonormal basis for U1 and U2. As long as I have some orthonormal basis whose span is exactly that of U1 and U2, then I am good, because I can then project onto that orthonormal basis. In other words, what I am saying is that, so when we started with A and then we did Q transpose A, here I initially assumed Q itself was U1 to UK, right. So Q transpose was just U1 to UK. But what I am saying now is that, well, yes, if it is U1 to UK, then things happen very smoothly, but we don't have U1 to UK. But do we really need U1 to UK? Well, all we need is that, what am I going to do this? I'm going to do the SVD of this and then pre-multiply it by Q, which means that effectively I'm doing QQ transpose, which is U1 to UK, which means that this matrix is just a projection. This is projection onto this LO subspace given by U1 to UK. Now, if I had a different Q, somehow magically I can come up with a different Q which need not have U1 to UK but still has orthonormal columns. such that the span of Q equals the span of U1 to UK, then I am happy, because any such Q whose span has this property, I can take such an orthonormal Q, do Q transpose A. For instance, think of it as I am rotating U1 and U2 by 45 degrees, right. So, this is U2 tilde, this is U1 tilde, right. So, because they are rotating in the subspace itself, the span of U1 tilde and U2 tilde will also be the same LO subspace. So, I am okay to even use these two vectors as my Q, and then I will do Q transpose A, do the SVD for Q transpose A, and then lift it back using the same Q, right. So, the key property that I need here is that I need somehow an orthonormal set of vectors, a basis. I mean, I should not say a basis for the subspace, but think of it as an orthonormal set of K, orthonormal set of vectors, or some orthonormal set of vectors which contains the span of U1 to UK. That is my goal. Getting U1 to UK itself is going to be hard. Well, that beats the point of doing SVD, right. So, because to get U1 to UK, I need to do SVD of A, which is what I am trying to avoid in the first place. So, I cannot do that. But by observing that, as long as I can get a different orthonormal set of vectors whose span contains what I want, U1 to UK, then perhaps I am still okay. Now, the question is there an easier way or a computationally efficient way to achieve that? The answer, of course, is yes, and that is where we are going to use the power of randomization. So far, all we have said is that we can do SVD quickly if you know the subspace to project to, such that you do not lose any of the information in the top case singular vectors. How to get such a subspace? Well, that is where randomization is going to help us enormously. So, next we will start looking at how we can use the power of randomization, like how we have used in JLemma, like how we have used in locality sensitive hashing. We are going to use similar ideas, but carefully crafted ideas. The randomization itself is going to be super simple, like how in the other cases as well. But then the reason why the randomization works is because randomization beautifully captures the needed structure, and how it does that we will see next time. Thank you.